new computations and do new kinds of big data if you switch over to SSDs. And that's essentially the message of the talk. Whoever wants to leave now can leave. I like this graphic. It's, when you think about big data, what is really growing? Right? The number of emails isn't really growing. It's about static. The number of clicks on the internet, it's about the same. The number of tweets isn't going to grow that much. What is going to change is the amount of metadata. Right? So what you can say about a collection, what you can say about an audience, how you group things, what you can say about it, that's the essence, I think, of big data and what is driving big data infrastructures. It's the data scientists who can look through all of these data and create more and more diverse data sets and more valuable data sets. This is why metadata is really the explosion in data that we will have over the next few years. The tiers that we tend to see and tend to focus on, a lot of people today are talking about your analytics tiers. What we see within our customer base is analytics tiers with a variety of different databases, each because those analytics take different forms and have different optimizations. Like what Paco was just talking about in the previous. There's certain queries that he's going to be able to do 10 times, 100 times faster than any other database. On the other hand, there's other data layers that perform their queries better. There's a lot of mix and match that happens in analytics in order to create this different set of metadata. However, if you want to use this metadata, right, if you want to use what you've created as a data scientist, there's really two paths. One is you're going to be creating a dashboard for someone, right? So there's going to be some business use case, and hey, I want to see a graph, and I want to know where to place a new store, where to buy a new wind farm, that kind of data, where to walk in Palo Alto where the trees are, right? But a lot of the data, and where I think there's been an underrepresentation in big data, is on the front side tier where you have automatic use of that data. So this is where the models you're creating are being used on the front line of an application tier. So what are the different tools that you're going to use across this landscape? Well, app servers, a lot of new good work there in the last 5 years. Analytics, Hadoop is the big thing everyone likes, but there's also a lot of new technology there. The front-side database land has also changed dramatically. There's still a lot of folks using sharded MySQL, and that's the technology that a lot of folks know. You shard out horizontally, and then you go up vertically with cache and tier. But then there's also all the NoSQL providers as well, right? And that's where Aerospike fits in. So what about SSDs, and what makes SSDs interesting? What makes SSDs interesting is the random access nature. Databases, traditionally, the relational databases and the analytic databases that you're used to are optimized for streaming. That's what's fast with rotational disks, and that's what we've all lived with as a storage layer for, 25, 30 years, maybe more, right? So the landscape changed dramatically when SSDs were introduced, because now we have a storage device that's like memory, that has a lot of the random access characteristics, but still has a lower price and has persistence. So what this means for these front-side technologies is you're able to do much more random access and random algorithms as part of your models and data sets. If you need to touch 100 data points to actually come up with a combined fraud score, for example, you can now do that because, well, if your front side is taking 35 million transactions per day, basically, front side fraud looks per day, and then you're doing 100, well, you've got to do 3 billion transactions a day. That's a lot for a traditional rotational-based system. It works in memory, but what if you need terabytes, right? That's where SSD comes in, because the in-memory characteristics have the lower price. I'm going to actually skip forward a little bit here. So one of the issues people tend to think about with SSDs is how expensive they are, right? You see a disk and you go, rotational disk is at 10 cents a gigabyte, and $10 a gigabyte is where enterprise-grade SSDs were about a year ago, 12 months ago. But the landscape has been evolving very, very rapidly. We've gone through 3 generations of SSDs back from the Intel X25 about 2.5 to 3 years ago, through to Intel's S3700 generation, the Taylorsville series that was introduced 2 months ago. And I just picked Intel not because they're the best, they do actually have some great offerings, but everyone has followed with similar offerings. So prices have come down in enterprise drives. Fusion IO is also priced at around $15 per gig, to numbers in the $1 to $2 per gigabyte. At that point, SSD is a very interesting performance tier between main memory and rotational. And at that price, just start multiplying. Okay, so if it's one, and then I need to, I need to double up, for example, to do high availability. I need some extra storage capacity to handle, extra data as I see it. This price difference really becomes a pretty attractive proposition for building terabyte scale at these kinds of IOPS. Right? So what you can now do is build on a single vertical server 1 million IOPS. And that's only happened really in the last few months. There's now a machine in Dell's price list called the R720XD, which has 24 different 2.5-inch bays in the front. And you can then easily put 20 2.5-inch drives in the front. And as long as you use the right card, Dell's been working on some issues with their RAID systems. You can actually get up to 500K in the front side of your database. And what I'd like to leave you with is that changes the algorithms and changes the models you can use. So I was talking to someone at the thing last night about how you can do NLP classifiers and decision branching. Right? So with each step in your tree of decision branching, well, let's say you have to go and get another 100, and go and get another 100, go and get another 100. Well, because you've got different NLP branches. You can put those now in database and use a much larger classifier set. Maybe you can go from a 1-tuple to a 2-tuple to even 3-tuple algorithms. Once you have the capability of storing billions upon billions of objects at this kind of speed at a reasonable price. So what does this then lead you to in terms of analytics architectures? What it leads you to is, if seeks are so cheap, you start thinking about a system, a clustered system, where instead of thinking about SQL and MapReduce as two separate things, it would be nice to be able to filter your MapReduce and have MapReduce not in a streaming sense, where it's a table scan, but allow it to randomly skip throughout your data set. So imagine a table which is taking a very high amount of writes, but is also capable of keeping, say, a most recently written field. And you want to only do a MapReduce style job or query over the last 5 minutes worth of data, but still keep an entire aggregate of 30 days. Well, with an architecture like this, you can keep the data in place, simply update that index, which is in memory, and then be able to very quickly go through seek, and just pick out a smaller subset of data. So with a MapReduce architecture that is capable of doing pre-filtering on the front side before it unpacks the data, instead of normally writing the kind of map job where the first thing the map job does is check a timestamp and then bail, right? You still have to get all the data there. Instead, what you do is you only select out and only pick the portions of data to be used. This is the kind of generational difference that can happen with SSDs. With SSDs, you don't have to think about it as a streaming table scan. Now, in cases where you really want to see the entire chunk of data and you really want to stream through, that's still going to be the kind of technology where Hadoop and table scan is most appropriate. But with the ability to have secondary indexes in a clustered system and select out just the rows you need, you are able to then build up different styles of algorithms. What we are thinking about also is, once you have user-defined functions, you can think about a customized database. Because so many of these queries do depend on it, and that's user-defined functions has been one of the greatest trends in memory databases in the last few years. Right? I think that Stonebreaker at Volt sort of opened all of our eyes to it, and good for him. That's what he's great at in the industry. But yeah, they've been around forever. Right? That's what Sybase's big claim to fame was as well. So with user-defined functions, which is part of what MapReduce is all about, is being able to invoke individual functions with more complexity. You're able to build out a more complex, essentially custom queries that run in database. So what we've done in our system is we have built out a lot of the simple SQL-style queries that you would like, your count, group by, distinct style operators, and have done that within user-defined functions. Pretty standard strategy. We found it to work very well in our architecture as well, partially because of the random access that SSDs bring. Let me go back to So what also happens with SSDs is when you start thinking about the algorithms that are appropriate for SSDs, like I said, you can skip around within your algorithms to a greater extent. So what does this mean for something like fraud detection? What it means for fraud detection is you can look at and evaluate multiple different algorithms in parallel in real time. So in the fraud detection case, you often have 100 to 300 milliseconds to make an informed decision. And the competition in fraud detection is making better and better algorithms to work within that subset of time. What that means is not only having multiple models coming out of your back-end analytics tiers, but also the capability of applying to those models a greater set of data. And that's where, if you have terabytes and terabytes of data, that you can use in each one of those models in real time. So, for example, in fraud detection, there's the what they call the velocity list, which is users or credit card numbers that are applying transactions and buying things at a high rate of speed throughout the entire world. And if you start seeing that, then you are detecting fraud patterns. Imagine if you could go one step further and do what happens in advertising and think about a cluster of credit cards, where you want to think of a cluster of credit cards like we think of audiences in advertising. And that cluster may have a certain velocity and show a different kind of fraud pattern. With the kind of random access that you get on the front side tier, new algorithms are possible. Similarity calculations also become very interesting with SSDs. So the most common similarity calculation is a cosine vector approach, where you have several different vectors, each one of them with a set of items seen. And you want to find the similarity between those simply by counting through those vectors. The first thing you need to do is get the individual first vector, and then you need to get a whole set of those vectors, that second set. And those are going to be very random, right? That's the kind of algorithm where you do need to go and pick out maybe hundreds or thousands of different individual data components to be able to bring them into one model. That kind of cosine similarity score becomes very attractive with SSDs or in memory. The main difference between SSDs, of course, is the price and capability. So instead of having to stay with an in-memory system where hundreds of gigabytes are the common case, you might be able to now start thinking about similarity calculations over terabytes of data, simply within a smaller, within a reasonable budget for a startup project. So as we know, a lot of these algorithms, you don't really know if they're going to succeed commercially until you start trying them out. That's one of the other benefits of this, is being able to work with larger data in early stage projects. So how many of you guys are Amazon users? Pretty much all of you. So I do kind of have bad news for SSDs and Amazon, right? You all know that high I/O instances are out there. Unfortunately, the performance characteristics of those machines aren't that great, right? So what we typically see, we have, I think, 3 or 4 customers at Aerospike running on Amazon high I/O instances. And we can't really push those things past 20, 30,000 transactions a second. And they're incredibly hard to get a hold of. They're only in, I think, east or west. these are the kinds of optimizations that make sense either on some of the other hosted cloud providers, Rackspace, GoGrid, something called Data Pipe out of the East Coast. A lot of those guys have SSD instances that are very close to the speed of raw hardware, and they'll run hybrid cloud architectures where you can rent out individual machines for a data tier such as Aerospike, and then keep your virtual machines and your front-edge web service and calculation engine in a cloud methodology. But it's not Amazon. We're all used to Amazon here, I think it's at least great that Amazon has brought out the high I/O instances, and we do have customers using them. But at some point, you might want to consider either what you might be able to do outside of Amazon or folks who are using it in their own data center. I was talking to some fellow last night who said, they had been doing a lot of work in Elastic MapReduce and pushing Elastic MapReduce. When they shifted over to their own data center, it was, in his words, transformative. The ability to run on your own hardware, as simple as Amazon is, these guys were guys who were spinning up 100 instances at the drop of a hat to go do a job. He said, well, now I just have 100 bare metal servers, and I partition off parts of it. I still essentially reuse components very easily, but the performance that he's getting is much higher. Now, not all of us have pet data centers, and the operational benefits of using Amazon are, of course, huge. That's why we don't use it. But these kind of benefits of SSD can come primarily when you have your own data center or you're running managed hosting. A lot of those guys also haven't switched over to the new technology. That's probably an issue with Amazon as well. It's unclear whose hardware they're using, at least I don't know. And those 1.2 tera devices that they're running appear to be an earlier generation than what's available now. So for folks of you who do have access to your own data centers, who do have access to buying your own machines, this is an attractive alternative. Whereas in Amazon, this is similar to being able to create clusters in memory. So a lot of Aerospike's customers are in the world of advertising. And so it's a pretty fun job, even though advertising might not have the best odor in the world, because I get to sit in on and hear about different algorithms that are being used within our customers. And I won't, I make a point of not actually trying to share any individual algorithms, but the state of the art as of a few years ago was primarily using audience classifiers and segment populations. And the issue is that clicks and views are so rare within the greater population set that you have to be able to combine those. Right? So you need to be able to look at a group because then you actually have statistically significant data. And then you can create models for those individual segments. So what ends up happening between their backside analytics and their front side systems is they need to be able to run large Hadoop jobs to classify. And exactly how well they classify ends up being an important part of whether their advertising algorithms are effective. Then once they actually get those models with those segments, they have to classify the individual user population. These days in North America, that's about 2 to 4 billion users between mobile and display PC advertising. There's a lot of double counting. There's a lot of people coming in and being classified by different data sources, Yahoo IDs versus Google IDs versus private cookies. Because there's clearly not 2 billion users in America. There might be 2 billion devices. What we're now starting to see is work with IP address categorization with the possible coming of things like the do not track system. So if you can't track with client-side cookies, you're going to use what you can, which is device fingerprinting and where traffic is coming from on the internet in order to provide more targeted experiences. So what we see within this customer population is that these guys want to keep real-time components. So they want to keep things like, they need to keep what ad was last served on a given, to a given person, right? If you serve something once and serve it again 2 seconds later, we all hate that. We would rather see something a little better or different or something in that. So In those cases, immediate consistency is really important at the database tier. Right? If you have a system where a write might take 2 or 3 seconds to propagate, then you don't have that freshest data as someone is clicking through and getting different ads each and every time. So those are examples within that particular world, unlike fraud and matchmaking, where you really do want that real-time model and a combination of the back-end Hadoop Vertica style processing and a little bit of Netezza feeding into a front-side tier that really can run at very high speeds. Our larger customers in this area, the number of ads that are served or impressions that are available on the internet right now is running around 500,000 to 1 million per second. So you need to be able to efficiently create a front-side database tier with very high availability, as well as being able to serve 1 million per second with these data sizes. So what's happened generationally, again, is that with our customers, we've seen a lot of doublings. So guys that we went out with who were doing 100 to 200,000 transactions per second and doing 1 to 2 terabytes of data are now trying to push 12 to 16 tera, and the world North American advertising rate is getting up to closer to 1 million. Part of that was the addition of Facebook to the advertising infrastructure. They used to do all of their work in-house, and now there's part of what's called Facebook Exchange. So all those different ads that you see on Facebook are now vended out to third parties as well. So what we saw previously a year ago was things like densities of 400 gig per server being replaced now with 2 terabytes a server. And that's just 1 year later. Now, my crystal ball and the guys I talk to say that this is one of the last big generational shifts that we will see in SSDs. That there's a curve that has occurred where density has increased. One guy that I know, one company says, Flash is going to get weirder, it's not going to get faster. They have different algorithms for doing multi-cell combining, and it's going to drive up error rates, essentially, and not necessarily drive speed and performance. This is probably where we're going to end up, this kind of $1 per gigabyte, 100,000 transactions per second per device. We're going to be at this level for probably quite a while. We'll see this level of technology sink into the cloud providers over time. And it's not clear we're going to see another doubling or another quadrupling of price performance out of the SSD guys. The fact that the social network guys have made such a huge investment in SSD technology internally with their own database tiers that they don't really tell anyone else about is an indication that more people in this room should also be considering SSDs within their companies and their companies' infrastructures. So we know, for example, that the company Fusion.io, being a public company, has to disclose the size of their largest customers. And these two companies bought $200 million worth of Fusion.io cards, according to the public numbers. $200 million worth of cards, right? So what that means is, in order to present those fast interfaces and more flexibility, more customization, being able to read and write that fast, they had to write a lot of custom software to do it, and they have created this level of investment. So I'd like to talk for a second about Aerospike and our architecture. So we started about 4 years ago with the belief that SSDs were going to change how we all look at data. But that clustered architectures with scale out were still going to be important. So I was at a company where the primary data model was an in-house DRAM-based solution for doing real-time behavioral, as well as having a sharded MySQL solution. This was sort of on the front edge of Hadoop. I think today they would use Hadoop. And what I found was that maintaining that sharded architecture at that time was incredibly difficult for the ops team. And we had lots of business problems created by, oh, we can't add another column to the database. But we want to run a different calculation. We've got a new model. No, you can't add another column to the database. And that kind of pressure, I think, is what has led a lot of us down the unstructured data root, and all of the NoSQL providers, of which we're one. So what we've done is created a shared nothing architecture where it's very easy to drop new servers in. That creates good operational characteristics because clusters do break apart and you do have network failures in the course of average data center operations. You can think about this as sort of what runs underneath things like EBS or guaranteed IO EBS instances. We have a client layer, which will look very familiar to anyone who is familiar with, say, Memcache, except that it has more of the Redis characteristics of rich data structures on a column-by-column basis. And by adding things like user-defined functions, we get push and pop operators like that. So that's essentially the architecture that we've worked through. And one of the benefits of this is that we're able to get high consistency. So we haven't followed, in the NoSQL world, the attraction of a Cassandra-based system or a React-based system where writes come in and then they're replicated asynchronously. What we do is we replicate synchronously within memory, so any client has a consistent view of any given row. That makes application design a lot simpler. Since you're simply updating what's in memory and using in-memory queues, we can still maintain very high performance. The kind of performance that we've got is, one thing that we like to talk about is we like to talk about YCSB. Anyone familiar with YCSB, the Yahoo Cloud Serving Benchmark? One over there. So that's a really good tool for evaluating NoSQL, because you shouldn't trust anyone who looks like me standing in front of you to talk about their own performance, right? I wouldn't trust me. So YCSB is on GitHub. There's this company Thumbtack that that's worked with us, but is also Cassandra, DataStax, and Couch and Mongo partners. They took a look at YCSB. They actually fixed some bugs to allow YCSB to scale out properly. And their repository is up at GitHub as well. So this is a great way for you to just simply do some of the standard CRUD operations on a NoSQL cluster and try it at different providers. So what we found, first of all, with SSDs, that's sort of our specialty, so no real shock there. What we also found compared to Cassandra and Mongo is Cassandra tends to saturate on CPU early. And I don't really want to cast any aspersions on Java because one can make Java go fast. But Java is not very good at these kind of fast transaction operations. I find the most success in Cassandra, and I know there's a lot of Cassandra users here in Austin, when thinking about it more like a column database. And trying to use it as a row-based store, it's really not the best use of that particular tool. What we find with MongoDB is the single core nature of their solution seems to be a bottleneck for these operations. And there's a bunch of work that the Mongo guys will tell you about how they're trying to solve that in more recent versions. I guess they've got 2.4 coming out soon. But this is where we've seen so far. And Couch is written a lot like our system in memory. But Couch really hasn't specialized in SSDs like we have. So in any case, YCSB is a great tool to allow anyone to actually track down what the performance claims are of individual companies and individual projects. So I strongly recommend you go figure it out yourself, post a blog on it, and see what your data set size is and what your distributions show. One thing, it's really hard to demo a database. So one of my favorite database demos over time has been, there's Tandem from a number of years ago. This guy had this great demo where he would bring a Tandem rack on stage and he would take out a gun. And he'd be running a certain number of transactions per second and he'd shoot into the rack. And you'd see transactions continuing. And that was always my ideal of the best database demo. Unfortunately, you can't do that in most places. Maybe I can do that here in Texas. But we couldn't bring the entire rack down here. We have a rack that we use for this kind of stuff. So instead, you can just see a slide. The interesting point is what happens when we simulate a node failure, which is what's happening right here. Right? So if you take it down to an operational load, first of all, that's 1 million transactions per second out of memory running on this kind of hardware, very modest consumer-grade hardware. which is what we use in-house because we're cheap, to create, build our large cluster sets. What you end up seeing is very quickly, almost instantaneously, the load shifts over to the other servers and they rebalance. And that's, I think, one of the most important parts about a clustered solution is how it deals with failures. Because when it's a bright sunny day and there's no failures, pretty much everything goes good. So let me wrap up here and leave a little time for questions. So one of the great things about SSD is, I've shown that the companies like Facebook that are using a lot of personalization, a lot of personal streams, a lot of groups of people. Those guys are all using SSDs now. They've shifted over from in-memory architectures and caching layers into having a database that really understands SSDs and is capable of random access. Random access is, once you start bringing it into your architecture, really changes the algorithms you use and what you can think about. So our database is available, free version at aerospike.com. So check that out. So any questions about SSDs that I could answer? Yes?
When you were saying that you use commodity grade SSD in-house, is that something that is still pretty high-end, or is that something you can buy off the internet at Amazon, Newegg, whatever?
What we use in-house is actually a lot of the buy at Newegg stuff, and we've even recommended it to customers. So we have a benchmarking tool called ACT that's available in Github, the Aerospike certification tool. And we have a lot of great luck of low latency with the Intel 320s. The 500s actually kind of suck, and the 700s kind of suck, but the 300s were great. Unfortunately, they're no longer available. They've replaced them with the 330s that perform more poorly. In my view, that's probably Intel trying to segment their market a little bit better and not make great drives at the lower price points. We had a lot of luck also with the Samsung 830s. The 840s are still pretty good as well. We did some tests on the OCZ Vertex and their set. We found them to have some problems with reliability. They are fast enough, but we had one customer shift over to them for a while and found reliability problems. OCZs are still very good on the high-end enterprise drives, but not at the dollar price point.
Thanks.
Sure.
Yeah, I was going to ask a related question that how you compare SSD
So here's the interesting thing about writes. Perhaps I should have said this during the presentation. SSDs are asymmetric in their I/O patterns. And that's not how they've been sold to all of us technologists. They've been sold that you can randomly put anything anywhere. And that's not the reality of today's implementations. SSDs, if you think about the chips, you have to do these large block erases in order to write anything. But then once you get a read, you can skip around as much as you want. That fundamental chip architecture ends up cascading up through the tech stack. So what we found is that write speeds are okay as long as you keep to those large blocks and try to align yourself as much as possible with the underlying chip block sizes. You'll actually see when we run a system like the ACT tool, you can actually see at which point you get higher and lower performances depending on your write block size. So essentially what that means in database terms is using a log-based file system approach is for writing, but then heck, you can just read like crazy, randomly skipping throughout it. Ends up being the optimal database pattern. The other problem with writes is not just throughput, and a lot of the benchmarks measure throughput, but when you write, you end up impacting read speeds, especially latency. Because the way to think about an SSD is it's a giant garbage collector. So all the problems you have in optimizing Java implementations, you essentially have with these storage devices as well. They're not very predictable, which is one of the reasons why we've had to go through and create this tool and look at different firmware versions. And the other reason to stick with large blocks. Once you have large blocks, you have fewer objects in the Java garbage collection sets, so you get fewer problems on the read side. Yes?
So does your solution have replication across cluster data sets?
Yes. So it's a fairly standard methodology. creating both rings and star topologies, allowing you to replicate writes out on a table-by-table basis.
Must be doing that consistently, which you have a lot of agents.
Yes, is the short answer. Most people don't. It's a law of the speed of light. Regrettably, as a database vendor, I can't change the speed of light. So most people don't want to wait for an entire, coast-to-coast round trip in order to do your writes. And part of what you're getting with replication is, if one data center goes down, you still want to be taking writes at the data center that's still up. So consistent replication is usually not what folks want. They want asynchronous.
How do scans work?
Scans are actually a very interesting topic. So the system is not really optimized well for scans, right? It's optimized for these random use cases. So you can still do a scan, but you'll end up getting lower throughput for those use cases. So don't use this for Hadoop, right? So for Hadoop, you're better off with scan technology that's rotational based. This is for random access and for picking out those individual rows in cases where you have algorithms where row by row random access is optimal. Yes?
Following up on that, is that based on price performance? I mean, or can you still get faster sequential scans with the SSD?
Current technology is about 2 to 3 times faster. So yes, it is price performance is the short answer. So enterprise rotational disks are running about 10 cents. You just sort of look at Dell's price list for trays. If you go pure commodity, you can even get cheaper. So at 10 cents versus a buck, it's 10 times cheaper to get a rotational disk. The rotational disk for scans is, SSDs are only 2 to 3 times more expensive. So price performance, you get about 3x better on rotational
You
disk.
specifically mentioned low power on your slides. What about the power cost between SSD and
Rotational is a little better for power. The real big difference is in DRAM. Right? So I went to a conference where they were talking a lot about HANA. And HANA, you guys know, it's from SAP. So what they do is they have in-memory, where each individual server in their cluster has between 1 to 2 tera of DRAM. And the guys I was talking to were like, well, it's great, the prices are coming down on DRAM. To get a tera of DRAM in a box is only $50,000. And then I said, yeah, but I installed it, and it's taking 100K in power every year. So, that can be deceptive. So I think the real benefit of SSDs is power versus consumption versus DRAM.
a big use for SSDs is the swap?
Except swap is incredibly slow.
Well, yeah, I mean, you reduce your RAM significantly, but you reduce the price of and power.
Sure.
What are you finding in terms of how quickly the SSDs wear out, since they have a limited amount of price compared to the magnetic material?
There's a couple of interesting factors there. One factor is some of the drives have the capacity to tell you how worn they are and to run test loads against them, and some of them don't. And so the Intel drives, for example, have a special smart command where you can basically sample it and say how worn out it is. It doesn't give you an absolute percentage, and then you can run a test load and see how worn it has gotten. Because you don't really know under the covers with a given write how that has required it to shift around the data underneath inside the covers. So measuring is important. So what we found for our customer base is that the commodity drives in the last generation would last 2 to 3 years. And one of the benefits of a clustered style solution that we have is you've got your cluster, and if one of the drives fails, you take that node down, and you can do that under high load, drop in a new drive, bring it back up, and resyncs. So the kind of RAID solutions. So, but RAID itself often has, the RAID layouts are not often optimized for SSD. So they will often create higher wear levels, right? So write amplification is really your enemy. If you can keep your write amplification down to 1 or 2x, you'll find that a lot of the drives, even commodity drives, will work pretty well. If your write amplification factors are getting up into the 7 to 10x, then you're going to see drives burning out probably in the 6-month range. But it depends a lot on your use case. You can burn out one of these drives in probably about 2 or 3 days and sustain the writing if you do nothing but hammer with large blocks. So that's sort of one answer, is the exact way that your software uses it and your data pattern uses it. But what has also happened is there's sort of two outs. One is you can pay more for your SSDs, right, and use, instead of using MLC, use SLC. But one thing Intel did in their last generation, the Taylorsville drives, is they invented an entirely new kind of flash chip. And that, I can't remember what they call it, they have some fancy Intel proprietary name for it. It's like ESS, eFlash or something. And that stuff has a write capabilities that are probably 10 to 20x higher than any previous version. And they're still pricing it at the $2 to $3 price point. So that is one thing that will probably shift a little bit over time, is we're going to get higher levels of write capacity. But when we went through the math with a lot of drives, assuming you've written your code to not, for example, we don't use the file system. We found that a lot of file systems, since they're updating the metadata for the file at the same time, that creates a fair amount of amplification as well. So by staying away from the file system and being a little careful about how you're doing these large blocks and real-time defragmentation, you keep your write amplification down, then you do the math, and we're finding that it's actually very, very reasonable. The other benefit is, rotational drives fail a lot too, right? So it's not like they don't fail; it's apples and oranges. And the good news about an SSD failure is when it fails, you can still read from it. Unlike a rotational disk where the drive is the head is plowed into the drive. Sure, go ahead.
Oh, I have a follow-up, but it's not related to this. When you were talking about the edge limitations of the current flash technology, and that we're reaching probably our max potential and things will get weirder rather than faster, is that factoring in other completely different technologies like Memristor, or is that?
No.
Okay.
Memristor is a whole other ball of wax.
Okay.
And hopefully that'll come along and give us all a lot of excitement in the storage world as well. The good news is databases that are shifting to these new style of I/O patterns and not relying on synchronous, balanced I/O, right? Reads and writes are kind of the same in rotational disk and DRAM. You start getting imbalanced, like I was saying with SSDs. Memristors are probably going to end up with a similar kind of thing. So the good news is the optimizations we're applying here. But yeah, maybe in 5 years, Memristors will be a new flash. That would be great.
Thanks.
Sure. Okay, thank you.